In this video, we're going to look at solving trig equations, and I'll probably break this set of notes up into two excuse me, two videos, just because it'll get pretty long, I think, if I put it all together. So we'll probably have one video through example 7, and then another video through the rest of the examples. So our objectives are to solve trig equations, and what we'll notice is the first few equations we're going to look at involve a single trig function, and then we'll look at some where maybe it involves one trig function, but it's in what's called quadratic form, and you'll see what we mean by that when we get there. And then we'll look at some where there are multiple trig functions involved, and maybe we can use some identities to get to a single trig function. And then we'll also look at some examples where we can't solve them by hand, but we can solve them using a graphing calculator. All right, so first example here, it's asking us to solve the equation sine theta equals square root of 3 over 2. We want to both give a general formula for all the solutions and then list 8 of the solutions. And my approach on something like this is usually to draw a unit circle and to think about at least the quadrants in which sine theta could be square root of 3 over 2. If sine theta is going to be positive, we know we've got to be in quadrant 1 or quadrant 2. And if we're going to have square root of 3 over 2, we're going to have something like pi over 3 in quadrant 1 or 2 pi over 3 in quadrant 2. So those are two of the solutions here where sine of the angle is square root of 3 over 2. But keep in mind that if I add 2 pi to either of those solutions, or either of those angles, that's going to be another solution to this equation. So what we've got is theta equals pi over 3 plus any multiple of 2 pi, and also theta equals 2 pi over 3 plus any integer multiple of 2 pi. So this is the set of all the solutions, right? And if I want to list 8 of them, and then I don't want that k in there anymore. I want to choose specific values for k and list the solutions. So we could have pi over 3, 2 pi would be the same as 6 pi over 3. So if I add 6 pi over 3, I'll have 7 pi over 3. If I add another 6 pi over 3, I'll have 13 pi over 3. Another 6, or I could even subtract 6, negative 5 pi over 3. And then I could do the same thing with, if I start with 2 pi over 3 and add 6 pi over 3, that would be 8. If I add another 6, I'll have 14. If I subtract 6 pi over 3, I'd have, what, negative 4 pi over 3? So there are 8 specific solutions to that equation, but there are certainly infinitely many solutions overall. Right? So again, what I did was I drew my unit circle and I marked down all the angles where the sine theta would be square root of 3 over 2, and at least once around the unit circle, and then I added multiples of 2 pi to those solutions. In the next example, it's asking us to solve a slightly more complicated looking equation, and it's telling us a specific interval. We only want theta to be between 0 and 2 pi. So we don't want to list every solution, we just want, from these instructions, to list the solutions between 0 and 2 pi. So notice the last one, we started right away with sine theta is this value. we want to get to that form. We want to isolate cosine theta first. So we'll start with what was given. And isolate cosine theta. That means just get it alone. So cosine theta is going to be negative square root of 3 over 2. And then I'm going to do the same thing. I'm going to think, all right, if cosine theta is negative, I want quadrant 2 or quadrant 3. My reference angle would be pi over 6 over in quadrant 1. So this is going to be pi over 6 short of pi, which is going to mean theta is 5 pi over 6. And this is going to be pi over 6 past pi, so theta is going to be 7 pi over 6. And those are the only two solutions between 0 and 2 pi that satisfy this equation, so that's it. 5 pi over 6 and 7 pi over 6. So again, the key was isolate cosine theta and then make a little sketch of the places on the unit circle where the angle would have the right cosine value in this case. And then if we wanted all the solutions, we would just add integer multiples of 2 pi to each of these. But since we only wanted the solutions between 0 and 2 pi, this is all we've got. Okay, so the thing that's new about this one is that we've got a 5 theta in the mix instead of just a theta. But we're going to work much the same way as we did with the others. First we want to isolate the cos 5 theta. Let's start by writing our original equation. 2 cosine 5 theta plus 1 equals 0. If I isolate cosine 5 theta, I've got cosine 5 theta is negative a half. And so what I'm going to actually do is show where 5 theta would have to be. So I don't care what type of input this is. If cosine of this input is going to be negative a half, the angle is going to have to be in quadrant 2 or quadrant 3. And the reference angle would be pi over 3 in quadrant 1. So here we'd have 5 theta, the input, is 2 pi over 3. And here we'd have 5 theta, the input, is 4 pi over 3. Right? So what we really got is the all solutions we could list as 5 theta is 2 pi over 3 plus any integer multiple of 2 pi, or 5 theta is 4 pi over 3 plus any integer multiple of 2 pi. But we don't want to know where 5 theta is, we want to know what theta is. But this is the best way to get started. So figure out, don't worry that there's a 5 there yet. Just say whatever that input is, it either has to be at the location of 2 pi over 3 or at the location of 4 pi over 3. Get a general list by taking that and adding 2 pi, and after you've added the 2 pi k, then divide everything by 5. So I would have theta is 1/5 of this whole side, and here we'd have theta is 1/5 of this whole side, which is going to mean we'll end up with theta is 2 pi over 15 plus any integer multiple of 2 pi over 5. Or theta is 4 pi over 15 plus any integer multiple of 2 pi over 5. And I suppose to make that easy, we could get a common denominator. So we'd have theta is 2 pi over 15, and then if a common denominator here, we'd have 6 pi over 15 times any integer, and here we'd have 4 pi over 15 plus any integer multiple of 6 pi over 15. We don't want, though, all solutions, but it's the easiest way to figure out the solutions we do want. So we've got a list of all the solutions. Now we want to figure out the ones between 0 and 2 pi. So we've got 2 pi over 15 would be certainly one of them. And then we want to add as many multiples of 6 pi over 15 to that as we can. So if we add 1, we'll be at 8 pi over 15. If we add another 6 pi over 15, we'll be at 14 pi over 15. That's certainly less than 2 pi. 2 pi would be 30 pi over 15, right? So add another 6, we'll have 20 pi over 15, which we could reduce, but let's leave it like that for now. Another 6, we'd have 26 pi over 15. But another 6, we'd have 32, and that would be too big. So then we move over to 4 pi over 15. Add 6 pi over 15, that's going to be 10 pi over 15, which we could reduce, but we'll leave it for now. Another 6 would be 16 pi over 15. Another 6 would be 22 pi over 15. And then lastly, we'd have 28 pi over 15. And we can't add another 6 pi over 15 because that would bring us past 30. So we get these 10 solutions. Right, so again, it was easier to generate a general list of solutions and then figure out which from that list would actually be in the interval 0 to 2 pi. All right. Example 4 is similar. It's just that now instead of just a 3 theta, we actually have a shift, 3 theta minus pi over 4. But we'll do the same thing. We're just going to say, all right, cosine of all this stuff, I don't care how complicated it is supposed to be a half. So I'm going to mark the location on the unit circle, or the locations on the unit circle where cosine of an input is a half. So my reference angle would be pi over 3, and I can either be in quadrant 1 or quadrant 4. So here my input, which is 3 theta minus pi over 4, all that stuff I would want to be pi over 3 if I'm in quadrant 1. And that input, if its cosine is going to be a half, and if it's going to be located in quadrant 4, I want it to be, let's see, negative pi over 3 I could do, or I could do 5 pi over 3, but I'll do negative pi over 3. So my general solutions would be that I want that input, I don't care how complicated it is, the input should be either pi over 3 plus any integer multiple of 2 pi, or the input should be negative pi over 3 plus any integer multiple of 2 pi. Then, after I've got where the general solution for this complicated input should be, now I'll rearrange to get theta by itself. So now I'm going to work with this. I have 3 theta would be pi over 3 plus pi over 4 plus any integer multiple of 2 pi. And on the other side, 3 theta would be negative pi over 3 plus pi over 4 plus any integer multiple of 2 pi. I'm going to get a common denominator right here and then divide by 3 next. So 3 theta. If I get a common denominator of 12, this is going to be 7 pi over 12 plus, this would be 24 pi over 12 times k. And over here we'd have 3 theta is, this would be negative 4 pi over 12 plus 3 pi over 12, so negative pi over 12 plus 24 pi over 12 times k. And finally, if I divide everything by 3, I'll have theta would be 7 pi over 36 plus 24 pi over 36 times k. And on this side, I would have theta equals negative pi over 36 plus 24 pi over 36 times k. And again, I could reduce this 24 pi over 36, but I want a common denominator so that I can add these multiples easily. So I've got the general solutions, and now I want to, let's see, get the specific solutions on the interval from 0 to 2 pi, since those were the instructions. Alright, so if I start with 7 pi over 36, I want to add or subtract multiples of 24 pi over 36, keeping everything less than 2 pi and positive. So one solution will be 7 pi over 36. I can't subtract 24 pi over 36 because that would take me into the negative solutions, and I don't want that. If I add 24 to 7, I'll have 31 pi over 36. And I want to just stay less than 72 pi over 36. So if I add another 24, that's going to get me to 55 pi over 36. And if I add another 24, I would be at 79 pi over 36. So that's too big. Then I'll start with the other side here. Negative pi over 36, that's too low because that's less than 0. But if I add 24 pi over 36, I'll have 23 pi over 36, and that will work. If I add another 24 to that, I'll have 47 pi over 36. That's less than 2 pi. Another 24, we would have 71 pi over 36. That's just barely less than 2 pi, because 2 pi would be 72 pi over 36. So we get these 6 solutions on that interval from 0 to 2 pi. So again, we didn't worry about the complicated input. We just said cosine of something is going to be a half. Then that thing, no matter how complicated it is, has to be at the location of pi over 3 or at the location of negative pi over 3, or that angle plus any multiple of 2 pi. So we set up those general solutions and then rearrange things to solve for where theta would be after we had already added multiples of 2 pi. And then we figured out how many of those multiples we could add to stay within the interval 0 to 2 pi. One more now involving tangent instead. So example 5 here, we've got tangent of theta over 3 plus pi over 5 is 1. And we want the solutions again on the interval from 0 to 2 pi. So just like the others, I don't care how complicated this input is. I want to know where tangent of something is 1. So I'm going to think through, where is the tangent going to be 1? And the tangent is 1 for angles either in quadrant 1 or quadrant 3. And these are located pi apart from each other. So as long as I have the one in quadrant 1, I can just add multiples of pi to that, since the period for the tangent function is pi. So I'll just take this input is going to have to be, let's see, pi over 4 in quadrant 1, and then plus any multiple of integer multiple of pi added to that. So this input, if its tangent value is going to be 1, it has to be located at pi over 4 plus any integer multiple of pi added to that. So this is a set of all solutions. If theta over 3 plus pi over 5 is going to have tangent value 1, it has to be located at one of these spots. So then I'll add or subtract pi over 5 from everything. Get a common denominator. I guess that would be 20, right? So 5 pi over 20 minus 4 pi over 20 is going to be pi over 20. K pi would be 20k pi over pi. Sorry, pi over 20 to get a common denominator. And then I want to multiply everything by 3 to figure out where theta is. So 3 pi over 20 plus 60k pi over 20. So I've got my common denominator of 20. This is a set of all the solutions. I want just those solutions on the interval from 0 to 2 pi. And I want to figure out which multiples of k can I use, or which integer multiples of this 60 pi over 20 can I use. So I want to stay less than 40 pi over 20, right? So it looks like I'd have 3 pi over 20 as my starting. And if I add even one of these, I'm at 63 pi over 20. That's too big. So this is the only solution. Right? Makes sense because the period for this function with the theta over 3 would be actually 3 pi. So we're not going to get back to that same tangent value on the interval of length 0 to 2 pi. Okay. So we just get one solution on that interval, but we also over here, for reference, had a list of all the solutions. So example 6, it includes in the instructions to find the solutions using a calculator, but you want to be able to figure out for yourself, when do I need a calculator and when do I not. If I've got something like cosine of theta is 0.3, we don't know any angles offhand whose cosine values are 0.3, so we would need a calculator for that. Right, so only if we have a value like 0 or square root of 2 over 2 or square root of 3 over 2 or change the signs on those are we going to be able to solve an equation without a calculator. So here we've got 0.3. That's not one of our familiar cosine values. So, whoops, we're going to take a graphical approach. So if we do a graph including just one period for this function, we can see how many solutions there are on one period and then add integer multiples of 2 pi to those. So let's graph this, and we've got cosine of theta, we'll have cosine of x, and we want to know where it's 0.3. So I'm going to do 0.3 for my y2, and that's going to be a horizontal line. The window I'm going to choose is just 0 to 2 pi. I'm going to have my x scale be pi over 2, just so the tick marks are nicely spaced. And I know this is only going to go as high as -1 and 1, so I'm going to move my y min and max to -1 and 1. Maybe I'll do 0.1 for the y scale. And I also want to make sure my mode is in radians, which it is. Alright, so quit that. We'll take a look at the graph. And it looks like there are two spots where the angle, cosine of the angle is 0.3, which is what we expected. One of them would be in quadrant 1 and one in quadrant 4. Right? So then we want to go to calculate, which is above the trace button. We want to find the intersection point, the first curve, second curve, and then move closer to one of them. So that's telling us 1.266 and then 0.3 for the y. Try to do a screenshot of this. Alright, so now that we've got this screenshot, let's do some writing on this. So now I've got one of the solutions would be theta is about, it says round to 2 decimal places, so we'd say 1.27. And this one, without going through the intersection, that's going to have to be 2 pi minus that angle, right? Because of symmetry of our unit circle. So if we've got one angle here, the other angle there, if this is 1.27, this one is going to be 2 pi minus 1.27. So you could certainly just go through the intersection point on your calculator too, but we can use symmetry to figure out that value. So one set of solutions would be, I guess we just want the interval 0 to 2 pi. If we wanted all solutions, we would add just 2 pi k to this. The other one, we're getting, if we did 2 pi minus 1.27, you get like 5.01. So, two solutions on that interval from 0 to 2 pi is what they were asking for. Alright, so now cosine or cosecant of theta equals -6. We don't have a cosecant button on our calculator, but that's the same as 1 over sine theta. So we could either just graph 1 over sine theta, or we could actually graph sine theta equals -1/6, and that would work too. So let's do a cosecant graph. So y1 we'll do 1 over sine theta, and we'll do y2 equals -6, and then we'll look for the intersection points. So 1 divided by sine theta, or sine x, and then -6. The period for cosecant is also just 2 pi, and they asked us for the solutions in the interval 0 to 2 pi. So that's what we want for our x min and max, 0 and 2 pi. And then for the y min and max, we want to extend this a little. We want to at least include -6. I'm going to do -10 to 10 and have the scale be 1. Remember that this graph is going to have vertical asymptotes wherever sine theta is 0. So at 0 and pi and 2 pi. Let's take a look at the graph. So it looks like we see two spots where the cosecant value is -6. So if we go through and do our intersection, when we do, I've got to be more careful about that. I think that this did give us an intersection point. Sometimes you need to be careful about which part of the cosecant graph you're on, but it looked like this branch was the one I wanted. So it looks like we've got an intersection point at 3.31 if we round to 2 decimal places, and then -6. Copy that quick. Oops. Try to paste it there. So now we've got, if this one is 3.31 roughly, so we've got one solution. This one by symmetry would be, we'd want to figure out the difference from pi, right, for this one, and then take 2 pi minus that. So we would do 3.31 minus pi, figure out what that is, and then do 2 pi minus that. Right, because one of these solutions is going to be in quadrant 3 and the other one is in quadrant 4. So 3.31 minus pi would give us the reference angle, and then we want to do 2 pi minus that. So this ends up to be the same as what, pi minus, or 3 pi minus 3.31. So 6.11 roughly. And again, if we were to go back to our graph and do an intersection again, we're on that first curve, that's the one we want. Second curve is that -6, and then our guess, we want to move over closer to this other one. And we're getting looks like it would round to 6.12. So I would accept 6.11 or 6.12 on a test. Just depends on where you round and how you get to the solution. Okay, then we've got a word problem here about the Ferris wheel. So we're given that in 1893, George Ferris engineered the Ferris wheel. It was 200 feet in diameter, and what we're told is the wheel makes 1 revolution every 40 seconds. And so this function represents the height of a seat on the wheel as a function of time, where t is measured in seconds. The ride begins when t is 0. So the first question is, during the first 40 seconds of the ride, at what time t is an individual on the Ferris wheel exactly 125 feet above the ground? So we would want to solve putting 125 in for h of t. So let's see, we'll subtract 125 from both sides, and we'll have 0. Divide everything by 125. And if sine of this stuff is going to be 0, then that stuff needs to be located at either 0 or pi. So we could have that 0.157 t. Oops, I added a t in there that shouldn't have been there. Let me erase that. So this input should be any integer multiple of pi, right? 0 or pi or 2 pi or 3 pi. If we add pi over 2, and divide by 0.157, we'll get 10 seconds. And then if we add multiples of pi divided by 0.157, .30 seconds. And if we add another, we can see that was just basically 20 seconds that we added on. So another multiple of that is going to take us past during the first 40 seconds. So we'd say t equals 10 seconds and t equals 30 seconds. And then the second part is asking us during the first 80 seconds of the ride at what time t is an individual on the Ferris wheel exactly 250 feet above the ground. Let's think about this one a slightly different way than we did the last one. Let's think about this graph. The middle of this graph is going to be at the height 125 because it's all been shifted up 125 units. And the amplitude is 125, so it's going to go as high as 250 and as low as 0. The period is 40 seconds. So the period divided by 4 is going to be 10 seconds. When t is 0, we can see that we've got h of 0 is 125 times sine of negative pi over 2 plus 125, which is 0. So we start at height 0. There's no reflection in this sine graph, so we're going to go up from there. So we could look at this as a shift also, but instead of looking at it as a shift, what I did was just figure out what are we at 0, and then so that's what this graph is going to look like, right on the interval from 0 to 40. So we could have figured out the first part by thinking about this graphically. We solved it analytically instead, but the graph has to look like this. They tell us the period is 40. There's some rounding to get this 0.157. Really what they should have done would have been like 2 pi divided by 40 to get that. They left it exact. So now if the question is, when is the Ferris wheel exactly 250 feet above the ground? That's going to be at the height of the ride, so at the max height. And it looks like that's going to be at 20 seconds, and then it would be again at 60 seconds. Right? We can think about it graphically. And then the last question is during the first 40 seconds, so back to 40 instead of 80, during the first 40 seconds of the ride, over what interval of time is an individual on the Ferris wheel more than 125 feet above the ground? So if we go back and think about our graph, between 10 seconds and 30 seconds, the individual is above 125 feet. All right, so that's the last example I think for this video. I'll make a separate video looking at these further examples where we have either more than one trig function or a trig function involved in more than one term, where they get a little more complicated.